Hello, I'm Michael Zanis. The purpose of this video is twofold. In the first part of the video, I will be giving an overview of the strategy that we're implementing to develop ADSL transceiver chips. And in the second part of the video, we'll go into the laboratory and give you a snapshot of our current activities on the ADSL development program and some of our near-term goals. In 1993, Aware and Analog Devices joined forces into a partnership under which we would develop ADSL chipsets that are compliant to the ANSI DMT standard. The goal of this partnership was to develop chips that would ultimately be mass deployable for ADSL consumer applications. The approach that we took to implement that goal was a multi-generational approach. I'll get into the reasons why we did that in a moment, but I'd like to go through the different generations that we've implemented and are in the process of implementing. The first generation that we implemented was based on a number of digital signal processors, multi-purpose, general-purpose signal processing engines, in which we implemented the digital functions that are necessary for a DMT ADSL transceiver. The analog subsection was implemented with a number of off-the-shelf analog components. This generation served the purpose of allowing us to optimize algorithms, get a system working in the lab that we can develop both understanding of trade-offs between hardware and software issues, as well as a general know-how of ADSL issues. The next generation, which is due for release in the next few weeks, we call Generation 1.0. And in this generation, we've migrated some of the functions that were implemented in digital signal processors to application-specific ICs, in particular two that you'll be seeing in the next part of this video. And that improved performance a bit of the system. It also reduces the size and the power, and thereby the cost of this solution. The final solution, or the end solution, is our Generation 2 product, which is going to be available in 1996 and involves integration on both the analog and the digital subsections to what we believe is a chipset that can be largely deployed for ADSL services. The purpose, or the reason for the multi-generational approach is there are a few reasons for that approach. The first of those is that we believe that it reduces the risk of getting to the end goal, which is the ADSL commodity level chipset. It also enables us to increase performance of this chipset in a staged way, so that with each generation we improve performance as we understand how to do that very well. The other advantage is that the interim generations that are implemented in this approach, Generation 1, for example, right now, are generations that can be used for demonstrations, for market trials or field trials, as well as for product prototyping, which we think is going to be important for priming the emerging ADSL market. At this point, I'd like to turn it over to the laboratory, where we're going to go over the current status of things here at Aware, and as I said earlier, give you some of our near-term goals.
Good morning. My name is John Langevin. I'm the marketing manager for the telecommunications group here at Aware. What we wanted to do this morning was bring you into our lab and demonstrate for you the hardware and chipset that we use in our ADSL Generation 0.5 development platforms. I'd like to introduce you to Marco Zanis. Marco is the project lead for our ADSL development program. Marco, how are you doing today?
All right, Jimmy, how are you doing?
Good. I thought what we would do is basically have you walk us through and explain the chips and the development platforms that we're using here. Give us a general description of the system, and if you can, demonstrate the performance of the ADSL Gen 0.5 chipset that we've got.
Okay, great. Right back here, we have a Generation 0.5 prototype chipset implementation. Prototypes like these exist here at Aware, at Analog Devices, and at a couple other of our close customers. The purpose of these prototypes is to really evaluate performance, test, debug, and optimize our chipset. Okay, this is the DBE board, digital backend board, that we said is the first of the two boards required for our prototype implementation of our chipset. On it, we have three DSPs. These DSPs perform all the digital and communications functions required for the ADSL modem. The rest of this board is actually does not actually perform any of the signal processing functions, and is used strictly for us to control these DSPs and for us to debug them and optimize them as well. So we have, like I said, 2 DSPs are actually required at the central office, 3 DSPs are required at the remote terminal, and these all perform the required functions by ANSI, standard.
So really the only part of the chipset or the only part of the transceiver are the 3 DSPs. This entire board is primarily used for monitoring and debugging, and the transceiver itself is only the 3 DSPs. Okay.
Right. So we require 3 DSPs, and actually the breakdown is there are 2 DSPs at the central office that are required and 3 DSPs at the remote terminal. Now, this board connects to the network on this side and to the analog front end that we're going to get into in a minute on the other side. Okay, John, this is the other board required for our ADSL prototype demonstration. We have this, we call this board the analog front end board, and it contains all the analog circuitry and a couple of digital ASICs that we built specifically for ADSL. In particular, we have 3 digital ASICs, a time domain equalizer ASIC, a decimation and interpolation ASIC, and then we also have, of course, the high-speed A to D converters, D to A converters, and all of the analog circuitry, the R's and C's to do the analog filtering, another ASIC that was built for ADSL, which is the line driver ASIC, the hybrid circuitry, and finally the connection to the line. So this would connect out to the line, and this would be connected to the network. As you can see, this board is deceptively large. It actually contains a lot of prototyping area, and there's a lot of space here to put probes in and debug the functionality of the modem.
But later on, when we talk about Generation 1, we're going to show an AFE board that's about half this size, that includes the DFIC chip, which basically takes 3 of these ASICs and integrates them into a single ASIC. Right. So later on, we'll show the much smaller board.
Okay, as I said earlier, now we're going to do a brief demonstration of our ADSL chipset platform. Back here we have a central office and remote terminal modems. They are connected. The 2 boards are connected together as I described earlier, and they are the signals, the ADSL signals then go on to the wire here, which is connected between the 2 modems. So this represents our ADSL loop. What we'll be doing is looking at the transmission through a couple of pieces of equipment here. This is a spectrum analyzer, and it's over the 1 megahertz band that ADSL uses. And we'll see the downstream and upstream spectra. We'll see the asymmetry, the downstream being a 6 megabit per second data rate, and the upstream being on the order of 96 kilobits per second. So if we'll also have this hooked up to the scope here, so that we can see the central office and remote terminal clocks locking together. This is the central office clock. The remote terminal clock is currently out of sync. You'll see it locked together, and then you'll see the modem go into steady state operation. So the first part is initialization, and you'll see the handshake and the modem training to the line and optimizing to achieve the 6 megabit per second downstream rate. So let's type in the command to start off each side of the modem. Central office is started off, remote terminal, and we see that the clocks are locked, and we see that the thing has transitioned at this point into a steady state. Now, if we look over here, we can see that through these monitors here, we can examine various things that are happening in the chipset. One thing that we have active is a bit error rate tester that tells us the performance of the modem. So if we look at, for example, what the upstream bit error rate is, we see that we've gone through 77,000 frames and we haven't received any errors yet. And likewise for the downstream. We can look at a couple other things that would just educate us a little bit on DMT and how it works. We can see the difference between the upstream and downstream spectra that I was talking about. This is the downstream transmitted spectrum. You see it's flat. It occupies the majority of the bandwidth. This is the upstream transmitted spectrum. You'll see that it's much smaller and it's carrying much less data rate. Now, one thing that's interesting is what happens when the downstream, which occupied the majority of the band, goes over the line. We see that the line has attenuated, and this is where the equalizer needs to correct these effects of the line. Likewise, the same thing has happened in the upstream as well. There will be some attenuation and phase changes due to the line. Okay, like John mentioned earlier, we're going to look at our Generation 1 platform, which is our first official release of software and chips. And here we see our analog front-end board. Remember, the previous analog front-end board had a lot of breadboard area for prototyping, and there was a lot of space between the parts. Now we've cleaned that up quite a bit, and one thing that has changed the size quite a bit is there is one single ASIC here that implements all of those functions that the other chips did on the previous platform.
So all the digital filter functions are now integrated into this single chip called a DPIC.
Right.
And as you can see, the board is roughly about 1/4 the size of the Generation 0.5 AFE, so we've dramatically reduced the amount of space required to implement the analog portion of the transceiver.
Right. So let's take a look at the digital board now. Okay, this is the digital board, which has not changed that much. It still has all the peripherals for debugging, but the main change is that we have a new ASIC. This ASIC right here, which is a digital interface ASIC, the DIA as we call it. And what it does is it performs many of the signal processing functions that were done before in the DSPs. It replaces one of the DSPs at the central office, one of the DSPs at the remote terminal, and it cuts down on the power and the cost of the chipset.
Okay, so for Gen 1, there's really only going to be one DSP in the central office and two DSPs in the remote terminal, even though there are three on this board.
Right.
But the chipset itself will only have one in the CO, two at the remote terminal, and then the DSP.
Right, and if we look at this board again, we can get an idea of the actual size that would be required to implement a full chipset. This breadboarding area here could have the DSPs and the DIA on it. And so this would be approximately the size, which is, how big is this, John?
It's about 6 inches by 7 inches total to implement a Gen 1 transceiver.
Right, the analog and the digital portion.
And as we said, Gen 1 performance is going to be full Category 1 performance of the ANSI standard. So we'll be meeting the 6.1 megabit per second downstream requirement and 224 kilobit per second full duplex requirement. But actually the chipset is going to be capable of running even faster than that.
Yeah, for lower loop lengths, it'll be able to go up to 8 megabits, possibly even higher. And I think that one important point is this is an ADSL standard compliant modem, and as such, it will operate over all CSA lines, unconditioned CSA lines. If your line meets CSA requirements, it can have bridge taps on it. The ADSL modem should activate and work without any problems and without any tech support.
To recap, we've gone into the laboratory and given you an idea of the current status of our development. A detailed presentation of our Generation 5 platform was given along with some performance demonstrations. That, as you know, is a platform that we use for development purposes primarily, and we gave you some of the features that we use to enable our future generations. Generation 1.0, which is a formal release, an overview of that was given as well. That's slated for release in the next few weeks. And Generation 2, which is our end product release, is currently being designed by teams at Analog and Aware and is slated for release in 1996. We hope you found this informative. Thank you very much.